Welcome to The Explainer. Today, we're unpacking a concept that is absolutely foundational to our modern world, and honestly, it's pretty fascinating. Have you ever actually stopped to think about how your computer's brain processes information? I mean, when you click a mouse, type a key, or load up some massive application, what is happening at the absolute lowest physical level of the hardware?
So how does your computer actually think? It's really easy to just take it all for granted, but the foundation of all modern technology relies entirely on the basic instructions we feed to our processors. At the core of every smartphone, every laptop, and every giant data center, there's a processor rapidly executing a list of tiny, microscopic commands. And the way those commands are structured dictates just how fast, how hot, and how efficiently our entire digital world runs.
Section 1. What is RISC? Okay, let's dive into this, because to understand how our devices got so incredibly fast, we really have to look at a fundamental shift in computer architecture. We're talking about RISC. You pronounce it RISC, and it stands for Reduced Instruction Set Computer. In electronics and computer science, this is a computer architecture that's completely designed around one core philosophy, which is to simplify the individual instructions given to the computer to accomplish tasks. Its entire purpose is just stripping away the bloat and making the commands the processor receives as simple and bite-sized as humanly possible. Section 2, RISC versus CISC. Now, to truly appreciate why this was such a real game changer, we have to look at what RISC was competing against. Historically, early computers relied on CISC, which is Complex Instruction Set Computers.
And this comparison brilliantly illustrates the core difference. With CISC, the computer is handed a really complex instruction. Think of it like trying to move a massive, heavy box all by yourself. It takes a lot of effort, it takes a lot of time, and you're probably going to struggle to get it done in one fluid motion. Well, RISC takes the exact opposite approach. A RISC computer might actually require more overall machine code to accomplish the exact same task, but instead of one massive box, it breaks the task down into many small, light boxes. The operations are so much simpler, which allows the processor to move them incredibly fast.
Now, you might be wondering, if RISC requires more machine code, doesn't that make it slower? Actually, no, not at all. The goal here is to offset the need to process more instructions by radically increasing the speed of each individual instruction. Because the instructions are so simple and uniform, RISC architectures can implement what's known as an instruction pipeline. So instead of waiting for one task to completely finish before starting the next one, a pipeline allows the processor to work on different stages of multiple instructions at the exact same time. It's basically a high-speed assembly line of processing, and it's just so much easier to achieve when your instructions are simple and predictable.
Section 3. The Load-Store Architecture. Now, what's really interesting about this is how RISC mechanically works under the hood to hit these incredible speeds.
It uses a concept called the load-store architecture. Here's how it breaks down in plain English. The RISC computer usually has a set of high-speed, general-purpose registers, typically around 16 or 32 of them. You can think of these registers like the processor's immediate workbench. In a RISC system, the instructions that actually perform the arithmetic and run tests, they operate only on these high-speed registers. If you need to access data in the main memory of the computer, you have to use separate, dedicated instructions that only load data from the memory into the registers or store data from the registers back into the memory.
So the absolute crucial takeaway here is this: one instruction equals exactly one function. It's just brilliant in its simplicity. You don't have a single messy command that tries to fetch data from memory, add a number to it, and put it back all at once. By enforcing this strict rule, copy a value from memory to a register, do the math on the register, move it back to memory, the CPU design is heavily streamlined. It allows for a few very simple addressing modes and, most importantly, totally predictable instruction times. This makes the design of the whole system incredibly elegant.
Section 4. The 1980s RISC Revolution. Let's trace how this all built up, because this elegant solution didn't just appear out of nowhere overnight. It took a massive revolution in the tech industry to bring this to life.
The conceptual developments of the RISC architecture actually started way back in the late 1970s with the IBM 801 project. But surprisingly, those early ideas weren't immediately put into use. It actually took designers out in California to pick up the 801 concepts and run with them in two seminal projects during the 1980s. Those were Stanford MIPS and Berkeley RISC. These academic projects proved the concept worked and were rapidly commercialized into the MIPS and SPARC systems. IBM eventually circled back, producing RISC designs based on further work on their 801 concept, which gave us the Power Architecture, PowerPC, and Power ISA. By the mid to late 1980s and into the 1990s, the floodgates had completely opened. This era brought us major designs like ARM, PRISC, and Alpha.
Section 5. Powering the Modern World. So why does all this tech history matter to us right now? Well, because that revolution directly shapes the world you and I interact with today.
The commercial utility of RISC was nothing short of explosive. Because these processors were so efficient and fast, they became the beating heart of early Unix workstations. But what's amazing is they scaled down beautifully too, becoming the embedded processors inside laser printers, internet routers, and countless everyday products. And they scaled way up. Today, RISC processors are used to power some of the most complex machines on the entire planet, including massive supercomputers like the Fugaku.
This architecture spawned a massive, incredibly varied family tree of processor designs. The varieties include things like the DEC Alpha, the AMD 29000, and of course, the ARM architecture, which is literally powering virtually every smartphone on the planet right now. We're also seeing it in the rapidly growing open standard RISC-V. The sheer variety here proves just how ubiquitous and adaptable this approach to computing really is.
So as tasks get more complex, how will simple instructions power the future? From a radical idea at IBM in the 70s to the architecture running the smartphone right there in your pocket, the philosophy of doing things simply and rapidly has definitely won out. But it leaves us with a fascinating thought to ponder as we push the boundaries of AI, spatial computing, and quantum processing. As our digital tasks become exponentially more complex, how will these brilliantly simple instructions continue to evolve and power our future? It's definitely something to think about the next time you tap your screen. Thanks so much for